First up, we have Professor Timothy Brown, and he is from University of Manchester Center for Biological Timing, and he's going to be sharing his research with us about the sort of non-visual effects and their impacts of light, non-visual effects of light and their impacts on human health and behavior with his talk titled Recommendations for Healthy Daylight Exposure. Timothy.
So it's really a great pleasure to be able to talk to you today about some of our recent activities devising these recommendations for healthy daily light exposure. And in terms of this general idea that light is beneficial to health, obviously this has been around for quite some time. But in terms of our scientific understanding and really what we need to be able to generate sensible recommendations, that's only come about relatively recently. So to give a bit of background to that, really the kind of key advances that spurred developments in this field started back in the mid to late 90s with observations that people and animals that lacked conscious visual perception, so blind people and animals, still retained certain responses to ocular light exposure. For example, acute reductions in the production of the hormone melatonin, effects of light on their circadian rhythms, etc. And not long after those initial observations were made, it became apparent that the reason they're retained in blind people is because there's actually a new type of photosensitive cell in the eye, beyond the rods and cones, the so-called intrinsically photosensitive retinal ganglion cells that have their own light-sensing protein, melanopsin. And we now know that these IPRGCs play a major role in generating a whole host of what I'll call non-visual effects of light, so effects on circadian rhythms, hormone secretion, sleep alertness, mood, and collectively we know these non-visual effects of light are important determinants of human health and well-being. But I guess the critical thing is, alongside the discovery of the IPRGCs, it was immediately apparent that this wasn't just something that was of scientific interest, but it was also of really important practical significance. And the reason for that is the range of wavelengths that this melanopsin protein responds to best are quite different from those of the cone-based visual system, and therefore the photopic function that we use to weight light energy according to its perceived luminous sensation generated in humans and drive our units like lux, lumens, candelas, etc. So given then that we've known about this system for quite some time, I guess you might wonder, well, why has it actually taken so long for us to begin generating recommendations based around healthy lighting? And the answer to that is that the IPRGCs are really quite similar to the other types of retinal neurons that are responsible for sending visual signals to the brain, in that they also act as a relay for signals from the rods and cones. So what this means then is that in principle, any of these IPRGC influenced responses could involve some combination of signals from any of the 5 opsin proteins in the human retina, so melanopsin, rods, short, medium and long wavelength sensitive cone opsins. And indeed, evidence kind of emerged that really the relative contribution of these different types of signals likely varied as a function of multiple factors, so intensity, duration, prior light exposure, etc. So as an initial response to this uncertainty, back in 2013, Rob Lucas and Bud Brainard organized the first international workshop on circadian and neurophysiological photometry. And the outcomes of that workshop was a measurement framework where light energy was weighted according to the known sensitivities of each of those 5 different opsins. The idea being that eventually this would allow us to compare data between labs and generate models that would allow us to predict the extent to which a particular light source might drive these responses. As some of you will probably know, that went on to form the direct precursor of the recent international standard for metrology of IPRGC influence responses from the CIE. And that involves some modifications to make the original framework fully SI compliant and compatible with our established photometric quantities. So for example, for any stimulus where you can define its luminance or illuminance, you can define an alpha opic, for example, melanopic equivalent daylight illuminance, and I'll explain that concept in a moment. So if you consider these two different light sources, so on one side we have natural daylight, 65,000 Kelvin. On the other side we have a white LED. If we wanted to calculate the illuminance of these, we'd weight the spectra with the photopic function, V lambda, sum across that, correct with a constant, and that would give us our value, which in these examples is 1,000 lux in both cases. And basically the principle is exactly the same for the equivalent daylight illuminance. For example, melanopic, we weight the spectra with the melanopic curve, sum across that, correct with the appropriate constant. And by definition, for natural daylight, this gives us a value also of 1,000 lux in terms of melanopic EDI. But for the white LED spectrum, because there's less energy in that part of the spectrum where melanopsin is most sensitive, when we do this procedure, the melanopic EDI is actually somewhat less than 1,000. So essentially what this is telling us is that on a per lux basis, the white LED is less efficacious at driving responses involving melanopsin compared to natural daylight. And as I'll go through the talk, I'll sort of highlight why that's significant. For now, though, it's worth stating that in line with how it was originally envisaged, this new measurement framework has facilitated a large range of both retrospective analyses of historical data and new hypothesis-driven investigations, which collectively have really very strongly pointed to a dominant role for melanopsin rather than rods and cones in driving these non-visual responses. So I'm just going to show you one example of that here. So this is data from one of the original action spectra studies, which investigated the propensity of light of different wavelengths to drive decreases in melatonin production in humans. And what you can see in the graph here is data from that study with the intensity quantified as photopic illuminance in lux. And hopefully you can quite clearly see that this really gives you no prediction of the extent to which those different light sources are going to drive the response. For example, 1 lux of 600 nanometer light does nothing, whereas 1 lux of shorter wavelength light can have a very strong effect. Importantly, though, if you take these same data and quantify them now as melanopic EDI, you'll see all of those curves superimpose on one another. And that's not true if you do a similar thing with any of the other alpha-opic metrics, which is just summarized on that bar graph there. So in simple terms then, melanopic EDI alone is giving us a very reliable picture of the extent to which light's going to drive this melatonin suppression response. And indeed, that's true of lots of other data sets out there as well. So given the kind of developments in the field then, back in 2019, we thought the time was right to hold a second Manchester meeting, second international workshop. So that was chaired by myself and Ken Wright from University of Colorado. And you can see all the participants here. And the objective then was to establish some consensus recommendations for healthy light exposure based on that CIE SO26 standard. And to briefly summarize our discussions, I think the strong consensus across the workshop was that, as I've just mentioned, melanopic EDI is the best available predictor of the magnitude of the non-visual responses that we have data on so far. And while, as I mentioned previously, there certainly is some data that signals from other photoreceptors, particularly cones, can play a role under some circumstances, really the existing data is conflicting both between studies that have analyzed different things and even between studies that have analyzed similar things. But the bottom line really is that where those effects have been seen, that the impact seems to be modest and in particularly limited to very early components of light exposure, which means that for the types of light exposure that we commonly encounter in the real world, so that's extended exposure to broadband white light, melanopic EDI really provides a very strong, reliable predictor of the magnitude of the responses that you're going to get. And just to highlight that point, here in this slide, this obviously summarizes tons of data, and it's not important to take in all of the minute details, other than to say that for a whole range of different light sources and different conditions, so different durations of exposure, different endpoints, effects on melatonin, effects on the circadian system, in all cases, melanopic EDI really provides a very reliable index of the extent to which the different types of light sources are driving this response. But probably the most important thing that comes out of this kind of analysis is that if you compare responses to a whole range of of different endpoints, so effects on melatonin, effects on the circadian system, effects on alertness, and you plot all that data on the same graph, you can see the range of melanopic EDI over which these responses occur is really very consistent between these different types of responses. So what does that mean? It means that really we've got a sensible quantitative basis now for generating recommendations for light exposure that are kind of recreating the biologically relevant signals these systems evolve to track, right? So it's long been realized that we want bright light during the day and low or almost no light at nighttime. But how bright is bright? How do you define bright? How do you define dark? This gives us a way of doing that. So here now you can see the recommendations that came out of the workshop itself. And so in the daytime, when obviously you want to maximize effects of light on the relevant biological systems, we recommend a minimum melanopic EDI of 250 lux at the vertical plane. So that should maximize responses. And similarly, during the nighttime, when light can have disruptive effects on the circadian system, sleep, etc. Obviously, you want to avoid these effects. And in that circumstance, we recommend a maximum melanopic EDI of 1 lux. And then obviously, in the intervening region in the evening, and we're recommending 3 hours before bedtime, when obviously you still need some light to see, but light can potentially have disruptive effects on your circadian system, hormone secretion, etc. We recommend a maximum melanopic EDI of 10 lux. Now, in aggregate, these recommendations are intended to provide realistic targets that will result in healthy daily patterns of light exposure. There are some additional considerations associated with these. Most important to flag here is that these are intended for adults with regular daytime schedules, right? So there's particular challenges dealing with shift workers, and we don't particularly tackle them in the present recommendations. But also more generally, we recognize that there are some groups whose sensitivity might differ from a typical healthy adult, so for example, young children or older adults. So we don't specifically tailor recommendations to different groups at the moment, although it's worth noting that in no way do we think adherence to the recommendations here should be detrimental for any of those groups at present. And finally, of course, it's worth pointing out that these recommendations aren't intended to supersede any existing guidelines around visual comfort, safety, etc. So we recognize there may be some circumstances where it's not possible to meet all of our recommendations, although in general we think they should be widely applicable and achievable. So just to illustrate that, this slide shows data from quite a large number of different studies that looked at the effects of lighting interventions in different settings. And what you can see here, first of all, is the kind of baseline control condition, the estimated vertical melanopic EDI. And what you can see is that in almost all cases, it falls below our recommended target of 250 lux for the daytime. And then in these studies, the interventions they use almost always brought light intensity above our recommended target and were associated with significant subjective and objective benefits in things like sleep, alertness, performance, mood, etc. Now, it's worth stating that in these studies, they actually used a range of different strategies to elevate daytime melanopic light exposure. Often these involved quite high color temperature, visually unappealing light sources. But of course, that really need not be the case. There are much simpler ways to elevate daytime light exposure. And obviously the most obvious one is to simply increase exposure to natural daylight, right? Just as an illustration, say if you're experiencing 300 lux, if that's coming from a standard 4,000 Kelvin white LED, then the melanopic EDI is going to fall below our recommended targets, where if all that light's coming from natural daylight, you'll be comfortably above. But it's worth noting that there will be some circumstances where it may not be possible to increase exposures to natural daylight, and in those circumstances, with appropriately engineered LED spectra, it may be possible still to meet our targets. For example, you could generate an LED with a spectra like this, with more energy in the short wavelength part of the spectrum, so it still has the same kind of visual qualities of a standard white LED, but now it has a higher melanopic EDI. The other thing to briefly note before I end is talk a little bit about our targets for the evening. So one concern might be, well, if you're limiting things to 10 lux melanopic EDI, will that really leave enough light to see? And so here, just to illustrate that point, this is actually data from a study that measured melanopic light exposure in people's homes in the evening with wearable spectrophotometers. And what I hope you can see here is that actually, in most cases, light exposure was already at or below our recommended target of 10 lux in the evening. And while it's not directly shown on this figure, actually, in many of the other cases, the higher values of melanopic EDI were associated with the use of lighting more enriched in shorter wavelengths, so higher CCT lighting. And really, that exposure could have been brought in line with our recommended target simply by switching to lighting which had a lower melanopic output, like commonly available warm white LEDs. So in general, we think that the targets are very achievable. So in terms of the kind of scientific basis of what I've spoken about today, for people that want more details, I'd strongly encourage you to look at our workshop document, which is currently available as a preprint. But to end, I should probably make the point that we certainly don't consider this to be the final word on the subject, right? So there's certainly plenty of scope in the future for tailoring recommendations to specific groups, the young and old, shift workers, clinical applications, that kind of thing. And obviously also, eventually, it would be nice to see these integrated alongside more conventional visual guidelines as part of a kind of more holistic approach to regulating how we light our environments. But I'll end there just by thanking the people that funded the workshop and obviously all of the people that participated in the workshop itself. Thank you.